Hi, good morning, guys, or good afternoon, or good evening, depend on when you are doing these notes with me. This is our first lesson, offline virtual lesson on chemistry. So, let's give it a try. I've done this once long time ago when I was having a TOC. So this is my second trial. So, let's see how it goes. So you guys, you can find these notes under your folder. You should go to the Teams one class notes, and you should be able to. I distributed this handout to you, so you should be able to get the handouts under your name. Um, and For this lecture, I have placed it under the content library. So this is we're working on unit 8 on the periodic table unit. You guys have done the package, and now this is the first lesson after the periodic table unit. Okay, so um, go back to the class notebook, and you should be able to find everything, all the recording, all the stuff, all the handouts, they should be there. Okay, so let's get started. Um, so we're gonna talk about how different atoms come together and become a bond. So this is on chemical bonding, how they bond together. So before we talk about that, you need to know there are actually two different forces that either drive the atoms together or repel them away from each other. So there is the attractive force, okay, and there is the repulsive force. So the attractive force, as you may remember, it's between the protons and electrons. Positive attracts negative, so they attract um, each other, and that's how they come together. But on the other hand, there are electrons all around the atoms, right? And the electrons, they repel each other. Okay, so that's called a repulsive force. So so I'm gonna draw two different atoms. So here we have the atom. Inside the atom is the proton, so that's the positive charge inside the atom, and then electrons are on the outside. Okay, so that's the first atom, and then the second atom, same thing, positively charged proton, and there are electrons on the outside. Okay, and again, there are two different forces. There is the attractive force. I'm just going to use red for that, okay? And there is the repulsive force. Okay? So when two atoms, they collide each other, they feel these forces at the same time. So they feel that there is the attraction between the electrons of one atom, and it attracts to the positive protons of the other atom. And same thing here. So that's the attraction. That's how the two atoms feel the attractive force, and they want to come together. But on the other hand, there is the repulsive force between the electrons. So there are more electrons in the atoms, but I'm just drawing two right now. Okay, so how do atoms come together to form a bond? So that's when the attraction is greater than the attractive force is greater than the repulsive force. Okay, so that, oopsie, spelling. So I hope you guys are just following me and copying notes. So before the lesson, I hope you guys, I should have said that earlier, but you should have the notes printed out, right? And then copy it down as we go through the lesson together, just like in real actual class. So, so that's when bonding happens, when the attractive force is greater than the repulsive force. All right. So, and now we're going to talk about different kinds of bonds. And as you remember, probably you should remember from grade 9, there are two kinds of bonds that you know. There is the ionic bonds, and there is the covalent bonds. All right. So as you recall, as you should recall, ionic bonds are formed between metals, one metal, usually one metal, and non-metals come together. Okay, so we're going to start with talking about ionic bonds. And so we're going to start with the classic example, sodium chloride. Okay, so it's table salt. So how do sodium and chlorine atoms come together to form a bond? So here it will be easier if we draw simple Lewis dot diagrams. So for sodium, if you remember earlier, sodium has one valence electron. All right, okay, so I'm going to use a cross to represent the one valence electron for sodium. And for chlorine, so if you remember the song, chlorine has a -1 charge. That means it has 7 valence electrons. Okay, something like this. And when they collide, if they collide in the correct orientation, the sodium wants to give its electrons away to chlorine, so it's want to get rid of the one valence electrons. And also chlorine, once it get the extra one, it will have 8, and that's an octet. 8 means 8, and that will make it happy. Okay, so when sodium and chlorine collide in the right orientation, sodium would give away its 1 electrons and become positively charged, +1. And for chlorine, I'm just going to draw the actual diagram. So for chlorine, after it gains 1 electrons from sodium, I'm just going to use cross here to represent that one comes from sodium. It will have a -1 charge. Okay, so again, it's the positive attracts negative, right? So positive attracts negative. This is the attractive force again, and that's how they bond together. Okay, so for ionic bonds, it's the electrostatic force that bond them together between the positive ions and the negative ion, and that's how they have this very strong bond together. Okay, so that's ionic bonds, and ionic bonds are super strong. And if you take a look at the melting temperature of sodium, for example, and you know, it's if you want to dissolve salt, table salt is super easy to dissolve, right? And they become ions. But if you want to actually melt the salt, you actually need a super hot Bunsen burner in order to melt the solid salt. Okay, so that's a very strong bonding because of the attractive force between the positive charge and the negative charge. Now let's move on to covalent bond, and as you may remember, covalent bonds are only between nonmetals. Okay, so we're going to start with a simple example as well to see how the bonds are together. So we have chlorine gas, Cl2 diatomic. All right, so again, I'm going to draw the simple Lewis dot structure for chlorine. We're going to do a review of Lewis dot structure very soon. In fact, next class, I'm going to have you guys review and also learn how to draw more complex Lewis structures. So I'm going to draw 2 chlorine atoms, each one with 7 valence electrons. Okay, so for these 2 are not metals. They don't like to give away electrons, but instead they want to share. They're going to share these 2. Oopsie. They want to share this pair of electrons here in the middle. Okay, so by sharing a pair of electrons, they form a covalent bond. So all these are lone pairs, the dots, those are called lone pairs. And the pair in the middle here, it's called a shared pair. Shared pair. Or bonded pair. And these ones here, lone pairs. And there are many of them. Okay, so one shared pair and many lone pairs. Okay, so that's the covalent bonds, and covalent bonds are in fact even stronger than ionic bonds. And if you take a look at some examples here, the melting temperature of some covalent compounds are in thousands of degrees if you want to melt them. And you heard that diamonds are forever, right? But in fact, they are not. So diamonds are only made up of carbon in very special orientation. But if you provide it with really super hot temperature, you can actually melt diamonds. They're not forever. So those are the two types of bonds you guys know. You should know from a couple years ago. And after the lesson, I want you guys to watch this YouTube. I'll post it right down on a different tab, but you will see it. Like it's the YouTube animation on how ionic bonds and covalent bonds are formed. So you guys can read that, watch that after the lesson. Okay, and then there's actually one more type of bonds. So this is a new one that you're going to be learning today. This is the next page, guys. This is the polar covalent bonds. Okay, before we talk about these bonds, I need to introduce another trend that you need to know from the periodic table. So remember from the periodic table package, you guys learned several trends, right? You learned about the size of the atoms. You learned about what did you learn? I forgot. So there are different trends that you were learning. Let me just pull it out. You guys should have completed this already, but we talk about the metallic property and size of the atoms and also ionization energy. So here I want to talk about the fourth one, which is called the electronegativity. Sorry, I need to turn off my phone. My mom is messaging me. So it's called electronegativity. So what exactly is electronegativity? So it's a number, okay? So basically it's just a number. It's a number, it's a value assigned to each element, and it will give you the sense of how much desire they want to gain an electron, okay? So here I put it as electron motive. So do they have a strong motive to gain an electron or not? Okay, so it's a desire to gain an electron. So the higher the number, more electron greedy. Okay, so it's like how motive, greedy, how greedy they want, how badly they want electrons. So tell me, you guys should know this. Pause for a moment. Tell me, on the periodic table, which elements tend to be more greedy for electrons? So I'm just going to give you guys a moment to think about which side of the elements like to gain electrons more. I'm sure you guys can answer that question. And yes, you are correct, I assume. It's the non-metals, right? So the non-metals, they are short. They are short of electrons, so they want to gain electrons way more. Okay, so from left to right, this side, we have an increased trend of increase in electronegativity. Okay, electronegativity. Oh, see. Yeah. Okay, and vertically in a column. Let's see. So from top to bottom, the electron negativity increases as we go from bottom to top. Okay? Hi guys, sorry I pressed something wrong, so I have to put this in two different sections. So, but I think it's going to be you're reading a PowerPoint, so there will be two different slides on this video. So yeah, so just continue. So again, left hand side they are metals, so they don't want electrons, right? So they're not greedy. But on the right hand side they are non-metals, so they are greedy for electrons. So they have high motive for electrons. Okay. Now if we just focus on one column and one family, as you remember, the size of the electrons, the size of the atoms, it's from top to top, we have the size is smaller, and the bottom, because they have more energy levels, they have bigger atoms, right? So in terms of how much they want electrons, if you remember from the periodic table package, the bigger the size, they actually feel less attraction to their outside electrons. So if they're smaller, they feel stronger attraction. So therefore, when we go from top to bottom to top, there's actually an increase in electronegativity. So once again, so the ones on the top, they feel a stronger attraction to their electrons, so they're more greedy to hold on to that electron, right? And then the bottom ones, they are big. The atoms are much bigger, and their outside electrons are like, just floating away, and just they don't feel a big attraction to the protons in the center, so they are not as greedy. Okay, so this is the number assigned to each element called electronegativity. Now, in fact, I'm going to show you this table here. So you on your textbook, page 333. So this is, I think it's chapter 12. I will upload it. I should have already uploaded to you guys. So this is from the textbook. This is the table that shows electronegativity for each of the elements. So take a look, as you may just be very well expected. Fluorine, it's the one that's most greedy, okay, for electron. It has the highest electronegativity because the fact that it wants one more so badly, okay. So from left hand side to just, if you look at just one row, right, like lithium is 1, fluorine is 4. So left to right, increase in electronegativity because non-metals just wants more electrons. And if you just look at one vertically, and lithium is a little bit stronger than francium. The fact that francium has like 7 shells, right? So it's a big atom. It doesn't feel its electrons as close to lithium. All right, so lithium has a little bit stronger in terms of electronegativity. So why do we care about this? Because the next bonding that we're going to talk about, called polar covalent bond, it's you need to know what electronegativity is. So it's a covalent bond still. So that means they are still sharing, okay? But polar, it means, I'm going to explain what this means. Basically, it means there's an unequal sharing of electron, okay? Sharing of electron. So they're still sharing, 1 or 2, 3 pairs of electrons, but the sharing is unequal. So the definition for polar covalent bond is that the shared pair of electron is drawn towards the electronegative atom. So let's say there are 2 atoms, and one of them is more greedy for electrons, so they are not sharing equally. So here we're going to talk about the classic example again, HCl. So there are 2 atoms. They are not the same kind of atoms. So one is more greedy for electrons, and the other one is not. So there's an unequal sharing of electrons. So here I'm just going to start with drawing the Lewis dot structure, right? Okay, so they want to share these two. They don't want to give it away, so they want to share it, right? So they form a bond, HCl, so the share pair between them. And yeah, so they are sharing a pair of electrons, but chlorine, if you think about the position of chlorine on the periodic table, it's more to the right hand side. It's very greedy for electron. So this is a more electronegative atom, which means it's more greedy for electrons. So it tends to pull electrons closer to itself. So if you think of this, you can think of it as a tug of war. Okay, so they are sharing, they are tugging this pair of electrons, but chlorine is stronger, it's greedier, so it tugs that pair of electrons closer to itself. Okay, so to draw this, there's some different ways that I can draw this. This is a single bond, so this pair electron is tugging closer, spend more time with chlorine. Okay. And for this, there's a special term that you need to learn. We draw this arrow. This is called a dipole. Okay, so for HCl, we are saying that this bond has a dipole. So what is a dipole? D-I-P-O-L-E. Di. Di means two. Okay, so that means it has two ends. So because the fact that chlorine tends to pull this pair of electrons closer to itself, there are more electrons to itself. Chlorine is a partially negative ion. Okay, so this is not an 8, but it stands for partially negative, like this. Okay, and for hydrogen, it's partially positive. Okay, so this is just a symbol that means partially negative. Okay, this is partially negative, and for hydrogen, it's partially positive. So you guys can, stop the video or go back, or if you don't understand anything, you don't understand some concepts, because dipole, it's a hard concept for people to grasp. But here I'm just going to use an analogy. Okay, so think of a couple. Okay, so hydrogen and chlorine, they are a couple. Okay, so they are sharing, a family together, a household together. But the fact that, let's say, chlorine, it's very let's talk about, so they're sharing some housework together. Okay, so they're doing some chores together, but one of them, they, like chlorine, it's doing the most work. Okay, whereas hydrogen, it's not doing as much. Okay, so because chlorine is doing more work and it's very, it's not very happy, and so it becomes more partially negative. Okay, whereas hydrogen, because it's just chilling around and not doing as much, it's partially positive. And just same as sharing electrons, because chlorine sharing more electrons, spending more time with that pair of electrons, it has become partially negative. Okay, I hope this makes sense. And just the proportion, they're not sharing 50-50. Okay, so chlorine is have more share, like 75, whereas hydrogen has only 25, so they are not sharing equally. So one become partially negative because it has more share. Okay, so this share pair of electrons, it's known as having a dipole because there are two ends. They are not like 50-50. There's one negative end, there's one positive end. Okay, so this is called the polar covalent bond. This is a little bit hard for you to understand, I know, but again, just play it back and try to understand my analogy of sharing household work 50-50. Right, that's a fair share. If not a fair share, then one person is going to be more upset than the other. Okay. Um, so so three kinds of bonds, and now there's actually a mathematical way to calculate it, as you may expect it, because there's actually a number assigned right here, that to these all the elements. So how to determine the bond type? There are three types. So we have a scale here. So we have a scale from 0 to 4. Okay, so one end is 0 and the other end is 4. Okay, so I'm just going to divide this up. 0 to 0.2 here, 0 to 1.7. Okay, so if the difference between the two atoms is between 0 and 0.2 in terms of electronegativity, they are covalent bonds. Okay? And if it's between 0.2 and 1.7, it's called the polar covalent bond. And if they have a big difference, so that's like ionic bonds, because one really don't want it, one really doesn't want it, and one really wants it so badly. So there's a huge difference in terms of electronegativity, and that's an ionic bond. So this scale is for, you actually need to do calculations on electronegativity. So we are doing it on offline lecture. This lecture I think is a little bit longer, so you can just pause it anytime, drink water and whatnot, right? So that's a good thing about online learning, I guess. Taking a sip of water. So we're gonna do a quick calculation here. So I turn to your textbook, page 333, I guess. Well, we have to have two screens to do that, but okay, doesn't matter. So we're going to go through the three examples we did today. So for example, let's do the HCl, this one we just did. So hydrogen, it's 2.1. Okay, so that's the electronegativity for hydrogen. And for chlorine, it's, where's chlorine here? 3.0. Okay, so you just do the calculation for electronegativity here, 3.0 minus 2.1, and you get 0.9. Okay, so 0.9, if you look at the scale, it falls in between 0.2 and 1.7, so therefore it must be a polar covalent bond. It's not sharing equally. Okay, so there's an unfair share of electrons. And for covalent compounds, like the one that we did, Cl2, so it's basically, Cl minus Cl, right? So you guys should know that, this must be 0, because they are the same, right? They are the same, so there's no difference. They are sharing it equally, so it's a covalent bond right here. And some of you may ask me questions like, oh, what if it's exactly 0.2 or fall in 1.7, like those boundaries? What would that be? Normally, when you do calculations, you don't fall in that range. Okay, so we usually have either 0 or anywhere in between. Okay, so the answer will be quite clear to you. And go back to the first one, sodium chloride. Where is sodium? Sodium, it's 0.9 here, and chlorine again is 3.0. So if you do, I'm just gonna do it here. 3.0 minus 0.9, you get a large difference here. So you get 2.1. Okay, so again, that would be classified as an ionic bond. Okay, so I'm going to do one more because some people get confused. For example, H2O. So here you're saying, oh, there's like 2 hydrogen and 1 oxygen. How do I do this? But you need to remember, like, these bonds, these differences are only between only 2 atoms. Okay, so for here we have oxygen bonded to 2 hydrogen. So we only care about 1 oxygen and 1 hydrogen. Okay, right here. So we can do a calculation here. So oxygen we have 3.5, hydrogen we have 2.1. Okay, so we can do a quick calculation. 3.5 minus 2.1. And that would be 1.4. Okay, So again, that will be a polar covalent bond. Okay. So I'm going to stop here. So remember to watch the YouTube video. It's really short, and I'm going to have you guys to do this assignment first. It's on your textbook, page 335, question 1 to 6. Okay. So I hope you guys like this video. If there's any comment, anything that you want me to improve on it and to make it easier for you, let me know. Just make comments down below. Okay. Thank you. I will see you guys soon. Bye.